Okay, we are going to do some stoichiometry problems at non-ideal gas situations, conditions, okay? Now, remember, stoichiometry from a while back was the problems that we did. We did a flow chart, remember, we did from mass to moles and moles to particles and back and forth. That's stoichiometry. It's the mathematical relationships using the mole idea. Well, we had one situation where we would go up to the volume boxes and we use the number 22.4 liters. That's if the conditions are good or ideal, which is the standard temperature being 273 Kelvin, or the standard pressure, or both being, standard pressure being 1 atmosphere, okay, or 760 millimeters of mercury, or kilopascals 101.3. But when we do a lab experiment, very rarely is your room at the same pressure. It's constantly changing every day. And the temperature in the room is not at freezing, so it's just 273. So a lot of times, almost all experiments occur in situations that are not exactly at STP or ideal conditions. So how can we fix that? Well, just recently, we learned about the ideal gas law, which is PV equals nRT. And so we want to put that together with our flow chart and show you a more developed flow chart that uses it at a different situation. So we got a problem here. Here's our problem. We have some methane gas that is being burned with oxygen. And we have a pressure and we have a temperature that's given. 1.32 atmospheres and a pressure of 325 Kelvin temperature. And it says how many liters of CO2 are produced according to this equation. So here we have our methane. We have our oxygen burning with it. And of course, combustion gives off CO2 and H2O. So this is a combustion reaction. Okay? And so now what we want to do is we want to figure out how much of each one. So to do the problem, we start off the same way we did. We draw a picture of the problem. So here's our equation. I actually balanced it, so I added my coefficients in to balance it. I go back to my problem. I start to pull out the information. We're given 100 grams of oxygen. So we'll put 100 grams right here. And it says they want to know in how many liters of CO2 are produced. So we're going to go to CO2 and we're going to go and find liters. So I begin the problem. I draw out my chart, and my chart, we're going to label one chart oxygen and one chart carbon dioxide. And then we're going to figure out the math that we need to get from one box to the other. We're given grams of the oxygen, 100 grams. We want to find volume of the CO2. So, as we mentioned, we have 100 grams of oxygen, and we need to find the volume of carbon dioxide. So, in our old process, we would just simply do 3 brackets in our jump in mathematics, but we cannot use this jump today of 22.4 because we know that gases, when the temperature and pressure change, we just learned from the gas laws, there's a change in the volume of the system. So the 22.4 liter only works if we're at 1 atmosphere and 273 Kelvin. Otherwise, if not, we have to add an extra little step that's PV equals nRT. So the ideal gas law makes this chart even more effective. So we're going to do one of those problems right now. So let's figure out how to get there. We are at mass. We want to get to this volume, but I have to use this math to get there. But I can still do 2 jumps in the flow chart. So let's start with that. Our given mass for oxygen is 100 grams. We're going to do 2 jumps and find the moles of carbon dioxide. Okay? First jump is mass to mole. We put mole on top. We're in oxygen's chart. Oxygen is 2 oxygens for oxygen gas. So it weighs 16 times 2 is 32 grams. Okay? And then we're going to go from mole to mole. So we need our balancing coefficient. The one we want goes on top. So we have 1 over 2. And then that will give me a mole answer. Okay? So 100 divided by 32. And then equals. And then again divided by 2 equals. Then what I end up is with 1.56 moles. And that puts me in the CO2 chart. Okay? So now I'm here, I want to go to here. Before, like I said, we just use one more bracket and we use the 22.4, but it's not feasible. So what we have to do is then write out our PV equals nRT gas law. And that gas law works no matter which way you go. If I want to start with volume and go to moles, I put my X by moles. And then just plug in the other information. But in this case, I'm here in the mole box and I want to go up to volume. So volume is my goal. So I want to get to volume, so I put X to the one I want to be in at the final answer. And then I just plug in the rest of the numbers. N is moles. I would need to find the mole number for CO2. Well, I just found that right there. So that's 1.56 moles. Then I would plug in the pressure and the temperature in R. Pressure was 1.23 atmospheres. Temperature was 325 kelvins. And then we have our R number, 0.0821. And of course it has all of our units in it that we need to use. And we have 325 Kelvin. Whoop. And so then we're going to rearrange our equation and get X by itself. How do we do that? We just simply divide out the 1.23 atmospheres. And then that leaves us with our X by itself. So to do the math, we're going to go 1.56 times 0.0821, push equals, times again 325, push equals, and then push divided by 1.23 and equals, and my final answer is 26.68 liters. And that would be my final volume for the CO2 gas at conditions that are not ideal, okay? So now you can solve that problem in any lab or any situation. They may not be at STP, okay?